Okay, then hello everyone to today's seminar on interval methods and control engineering. And it's my very great pleasure to welcome today Rachid Malti from the Université de Bordeaux, where he's a full professor in automatic control and computer engineering. And I think Rachid is very well known for his work on fractional systems, especially also concerning his MATLAB toolbox that he developed, or he is developing and working on. And his application focuses on lithium-ion battery modeling, decision planning for autonomous vehicles. And he is also serving as a technical committee member of two IFAC committees, namely the committees on modeling, identification, and signal processing, and also linear control systems. And now, Rachid, we're looking forward to your presentation on exponential stability analysis of linear irrational systems in the parameter space approach, where you will explain explicitly some constraint satisfaction problem. Okay, Rachid, we're looking forward to your talk.
Thank you very much. Thank you, Andreas, for introduction. So as you said, the title is Exponential Stability of particularly irrational systems. So these are systems that go a little bit beyond the fractional systems. And we are just using interval methods here in this particular case to find what are different stability regions of such irrational systems in the parametric space. So this is a joint work with Professor Milan Rapaic and also Vukan Turkulov from University of Novi Sad. The results are quite new. I would say not yet published, but there is a paper in HAL, which is the French archive, in case you want to have more details. Okay, so yeah, so just a word to say that I'm here in Bordeaux, in the east of France. Bordeaux is quite famous for its wine. Okay, so let's move a little bit. I will start with some definitions, first of all, and then I will move to some motivations. In order for everybody to be able to follow, so I started with some very known things regarding definition, for instance, here of a rational transfer function. So here you have a rational transfer function. So starting from this rational transfer function, everybody knows that we can assess stability of this transfer function by examining the roots of the characteristic polynomial. So we usually deal with characteristic polynomials, and we search for the roots of these characteristic polynomials in order to be able to conclude whether transfer function is stable or unstable. Okay, so now what happens in case we have an irrational transfer function? Then things become a little bit more complicated. So here you have an example of an irrational transfer function. Okay, so we may say probably that the characteristic function up to now it was called characteristic polynomial, okay, but now we don't have any more polynomials in the S variable, so we will be using this new name, which is characteristic function, instead of characteristic polynomial. And assessing stability of such transfer function is a little bit more complicated because it's a little bit more complicated to find all the roots of this characteristic function. You may even have other kinds of characteristic function, like the one which is here on the right-hand side. So in case you have exponential of 1 over s, so you may ask yourself the question whether you have to put this exponential in the numerator or in the denominator of the transfer function. So definition of a characteristic function is not as evident as characteristic polynomials. Anyway, the function f2 of s has an essential singularity at s equals 0, because s equals 0 is a singularity of f2, and it is at the same time singularity of the inverse of f2. So we may ask ourselves, what is the characteristic function of F2? There's even a third example here. If you consider the transfer function F3, then it has a branch point at s equals 1, because here you have a square root of s minus 1 divided by s plus 1. So in case you look for the impulse response of F3, then you have something like this with exponential t. And this exponential t is due to the branch point, which is right on s equals 1. So examining exponential stability of transfer functions like F3 is not as easy as rational transfer functions, because you have also to look to all the singularities of F3, either they are in the denominator or in the numerator. So this is the conclusion for this slide. We cannot assess stability of F3 by only examining the roots of the denominator. Okay, so here we are proposing a definition of a characteristic function. So a characteristic function must have all, all its zeros, all the zeros of a characteristic function must be poles of the transfer function. A characteristic function should have no pole, must have no pole, and transfer functions and characteristic functions must have the same essential singularities and the same branch points. Okay. So a characteristic function of a transfer function f of s can be derived by inverting f of s and multiplying by a given numerator s of s. Okay, in order to be able to respect all the three remarks that are here on the left-hand side. So in this sense, the characteristic function is not unique according to our definition. So there are multiple characteristic functions for a given irrational transfer functions, and they might be also multiple transfer functions for one characteristic function. But this is not an issue as long as we are concerned, because we are looking for a one-to-one correspondence between characteristic function zeros and transfer function poles. So we will be interested during this work on the characteristic function zeros. Okay, so we finished with definition of a characteristic function. Let's see some motivations of our work. I will detail here three kinds of motivations. The first one is related to distributed parameter systems, second one to time delay system, and third one to fractional systems. So let's start with distributed parameter systems. We are considering here a 1D diffusion, heat diffusion. So just assume that some heat flux is injected on the left-hand side of a rod. In the example that you have taken, it's an aluminum rod. So this rod might be of finite dimension or of infinite dimension. And then we are measuring the temperature at a given distance x0. Okay, so this phenomenon is governed by heat diffusion equation, which you may see here. So you have second derivative of temperature with respect to distance, which is proportional to the first derivative of temperature with respect to time. And we are considering Newman boundary conditions at x equals 0 as the injected heat flux is proportional to the derivative of temperature. So this system by itself is a stable system, because when you inject some energy in system, it doesn't blow up. Okay, but what if you consider that this system, which is represented in the right-hand side by transfer function g of s, is controlled by some control loop? So we are considering here just a proportional controller with some delay at the same time in the actuators and in the sensors. So by considering that we have a closed loop with some delays, the closed loop system might become unstable. So here is the proportional delay controller that we are considering, and the Dirichlet boundary condition at x equals L, we are considering that temperature is the ambient temperature that is just withdrawn because we are interested just in the dynamical part. Okay, so if you try to solve, if you solve heat equation in the semi-infinite spatial domain, then you end up with a transfer function that involves exponential of square root of Laplace variable. So here we have the exponential of square root of Laplace variable. And in the denominator, you also have a square root of Laplace variable. So the denominator corresponds just to a fractional integrator of order 0.5. But in the numerator, you have some exotic function, which is irrational transfer function. So putting this guy in the closed loop, you may compute the closed loop transfer function, and you obtain something like that. And this transfer function has a singularity, which is a branch point at s equals 0. And then we are also interested, we will be interested in finding all the roots of this characteristic function in terms of k, which is the gain of our proportional integrator, and in terms of tau, which is the delay of our proportional integrator. So we will be interested in finding for what values of k and tau this system becomes unstable. Now, if you consider finite spatial domain, then the transfer function obtained by solving heat equation involves some hyperbolic sine and hyperbolic cosine. The closed loop transfer function also has these terms. And finally, the characteristic function will involve some cosh and sinh of the square root of Laplace variable. So again, finding the roots of f is not as easy as in the rational case. So the main objective of our work was how to analyze stability of such closed loop transfer function that may involve some exotic transfer functions of the Laplace variable. Okay, so if you consider again just the semi-infinite spatial domain, and for the particular case when tau equals 0, so the roots can be computed analytically because we know how to solve this particular equation. Actually, all the roots, I mean, from this equation, when you equate to 0, you end up with this. And the solution of this equation is given by all the determinations of Lambert's omega n function. So all these determinations must fulfill the following condition on the right-hand side, as the arguments of square root of Laplace variable must all be less than pi over 2. Okay, so plotting the solutions with respect to k, so this is a kind of root locus. So for values of k that are less than 3000, our system, I mean, our characteristic function has no 0. And then a 0 appears from the plane cut. Here, plane cut is done from branch point 0 up to minus infinity. So a 0 appears from the plane cut for a value of k, which is equal to 3000. And then when you raise the value of k, then the poles split into two complex conjugate poles that move that way. And then we can see that the system becomes unstable when k equals 56,000. And then, yeah, the poles remain unstable. So for the particular case where the delay equals 0, we know that the system is unstable for this value of k. So regarding this first motivation, our interest is to analyze the exponential stability of distributed parameter systems. I mean, both of them, either in the semi-infinite or in the finite case, in the parametric space k versus tau, in both cases, in semi-infinite and finite spatial domain. So this is the first motivation regarding distributed parameter systems. Let's examine now the motivation regarding time delay systems. So the motivations are quite similar. We are considering two kinds of distributed time delay system. First one is a distributed delay. So we don't have just a single delay, but we have an integral of delays. So it's kind of distributed delay. And second one is delay of retarded time. So by computing Laplace transform of this equation, you may end up with this, this characteristic function. And here you already have it in terms of characteristic function. So second motivation is also analyzing stability of time delay systems. In this party, in the left-hand side, it will be versus k and tau parameters. And in the right-hand side, it will be versus tau1 and tau2. So we will show that our method works for ordinary delays, distributed delays, and retarded time delays. Third motivation concerns fractional systems. So for fractional system, you have here an example of fractional systems with fractional derivatives on the Laplace variable here. So in case transfer function is commensurate, then all the differentiation orders are integer multiples of a given commensurate order, mu. So we have a very important theorem regarding stability of commensurate fractional transfer functions. So the commensurate order must be between 0 and 2. And all the arguments of s to the power nu must be in a sector that's defined by this inequality. Here you may see an example. So in case commensurate order equals 0.5, then you have a sector here with an angle pi over 4. And if all the poles are in the green part, then the system is stable. If you have some poles in the white part here, then the system is unstable. Here, I must precise that we are talking about poles of s to the power of nu. So maybe there is a small mistake here. It must be s to the power of nu. Anyway, when we deal with incommensurate systems, take for example this one. So this one is not commensurate as pi and square root of 2 are real variables. So it's just impossible to determine stability using Matigno's theorem. So one might think, okay, I will approximate pi as square root of 2 using one digit, for instance, as is the case here. So in case you check stability of F1 using Matigno's theorem, then you end up with the conclusion that this system is stable. Okay, but instead of approximating pi by 3.1, if you approximate pi by 3.2, then you may end up with another conclusion. The system is completely unstable. So it appears clearly from here that you must look for other digits, here. So if you decide to approximate those two real variables using 3-digit precision, then checking stability using Matigno's theorem requires finding all the roots of a polynomial of order 3141. MATLAB knows how to do it, though it's quite difficult to solve, and we may question ourselves on the reliability of the result. And anyway, all the poles must satisfy this Matignon theorem. So from this example, it appears to be quite difficult to conclude on stability of incommensurate fractional transfer functions. And anyway, in double precision, you can never compute all the roots because you have polynomials of very, very high degree. Okay, so that's why we have some intermediate results also when the system is commensurate of order 2 mu, like here. And this is a funny result because it generalized what we already know in rational systems. If nu equals 1, we all know that the stability condition is that zeta must be greater than 0. So in this particular case, zeta must be greater than minus cos pi over 2 for the system to be stable. This is something that we have shown in this paper. There were also some other works regarding this particular system. Function G2 is incommensurate, function G3 is also incommensurate, So some papers dealt with using Cauchy's argument principle to try to find the stability conditions of these two systems. Okay, so our main objective here, and this will be the example that we'll be treating, is to analyze stability of F in the parametric space alpha 1 versus alpha 2. So we will be doing that by analyzing the roots of this polynomial. And we know how to compute the roots of this polynomial for some particular values of alpha 1 and alpha 2. So first of all, a plane cut is necessary from 0 to infinity, and all arguments of S must be restrained to this condition. So anyway, if we discretize, I mean, if we choose, first of all, alpha 1 equals to 1, and we choose some discretization values for alpha 2, so we have discretized alpha 2 with a step of 1 over 40, then we could compute all the roots of this polynomial versus alpha 2. So what we can see here, that there is a root that appears when alpha 2 equals 1. For values of alpha 2 less than 1, the system has, I mean, the characteristic function has no root. When alpha 2 becomes a little bit bigger than 1, then this root splits into two roots. Then we have a double root here when alpha 2 equals 2. And then the system becomes unstable for the first time when alpha 2 is equal to 2.8. This is the first time when two poles cross the imaginary axis. And then if for higher values of alpha, we have many loci that cross the imaginary axis. Okay, so yeah, so if you do another zoom here around this point, minus 0.5 and 0, then you can see also that roots appear for a given value of alpha. When alpha equals 3, then two roots appear, they split, and then they disappear in the plane cut when alpha equals 4. Roots appear for alpha equals 5, disappear for alpha equals 6. So some strange things like these ones might happen. So our third motivation is analyzing stability for fractional incommensurate systems, also in the parametric space. In this example, it's parametric space alpha 1 versus alpha 2. Okay, so I finished with the motivations. Let's now formulate correctly the problem. So considering an LTI system, so this LTI system might be rational, but it might be also irrational. We are considering different kind of LTI systems, and our formulation is meant to be universal for all irrational linear time invariant systems. Okay, and we are considering here some theta, which are the parameters of a characteristic function that belong to a given subspace of R to the power n. So the problem can be formulated as partitioning the parametric space into regions, such that for all k, fs theta has no 0 on the imaginary axis, and in each region, we must have the same number of zeros for fs theta 1 and fs theta 2 if theta 1 and theta 2 belong to the same region. So this will be done under some hypotheses, under 3 hypotheses. So I have 3 slides to explain 3 hypotheses. Let's start with the first one. So for every theta in the parametric space, fs theta must be analytic in C plus, I mean, must be analytic to the right half complex plane. Actually, the proof was done even for a given gamma. I mean, gamma is a vertical axis. So just assume gamma equals 0 in this presentation. When gamma equals 0, then we will have poles to the right or to the left of the imaginary axis. But anyway, in case gamma is less than 0, then we will be able to guarantee some exponential stability. In case gamma is equal 0 and we have roots to the right, then we will be able to guarantee exponential instability. Okay, so first of all, characteristic function must be analytic to the right of the complex plane. So again, just for simplicity, assume gamma equals 0. So for instance, this transfer function is excluded by the first hypothesis. This is transfer function I've shown in the first example because it has a singularity at s equals 1. Okay. So this is not permitted by hypothesis 1. Hypothesis 2 tells us that for all omega k z, there exists sigma. Okay, so yeah, this hypothesis, so we are assuming that we may have some singularities on the imaginary axis, again, by assuming gamma equals 0. So if we have, so we may have a finite number of singularities on the imaginary axis. These singularities are represented by red dots. So hypothesis number 2 excludes the fact of some characteristic functions may have poles that pop up from those singularities to the right half complex plane. So such a system are excluded from our study. So we should not have poles popping from this to the right hand side. So here we have provided a given transfer function k plus s to the power minus 3 over 2. So when k becomes negative, we are having poles that pop up from 0. So this kind of transfer function is excluded. And the third hypothesis excludes actually characteristic functions that may have poles that pop up from plus infinity. Okay, so this kind of transfer function may be encountered when you have non-negative delays, but this is something that is non-causal. So not very interesting, but we may have also some other examples. If you consider such an open loop transfer function, then its closed loop polynomial writes this way. And you can see that when k varies from 0 to -1, the root slides along r minus. So from 0 to -1, root slides along r minus. If you substitute k by 1, then you have a kind of simplification between this s and this s. So the model order changes. And then when k varies from 1 up to infinity, then the root slides along r minus from infinity to 0. And this particular fact is excluded from our study. So anyway, this system can be studied, but only for values of k that go from 0 to -1, because we are excluding by hypothesis 3 roots popping up from plus infinity. So, okay, so these were our main, this was our problem formulation. Now I'm going to present the results. So we'll start with the theorem regarding root continuity, and then we will see how we applied interval arithmetics to solve this problem. So regarding root continuity, so under hypothesis H1 and H3, given any connected subset S of t, if f is different from 0 for all omegas and theta in S, then any theta 1, theta 2, the number of zeros of f in C plus counting their multiplicity is the same as the number of zeros of S theta 2. What does this theorem say? Well, first of all, this theorem is an extension of Dieudonné's theorem to non-compact sets, because Dieudonné has already established such theorem for compact sets. And this Dieudonné theorem was used for time delay systems because those time delay systems don't have any singular points on the imaginary axis. But as soon as you have some singularities on the imaginary axis, then the set becomes non-compact. So we have extended this theorem to non-compact sets. And this theorem suggests that under the hypothesis H1, H3, that the zeros of f cannot suddenly appear in C+. This is something important. They cannot suddenly change multiplicity in C+ either. And the only way for the number of zeros in C+ to change is by crossing the imaginary axis. So this is the main result. I mean, the main result of theorem is summarized in these 3 points here. So this theorem suggests that if we can find for what values the poles cross the imaginary axis, then we can delimit all the stability regions. So the determination of stability crossing sets, the stability crossing sets are sets for which parameters involve some crossing of the imaginary axis. So yeah, for stability crossing set is defined in such a way that parameters belonging to T for which characteristic function equals 0 for some values of omega. So it allows characterizing all regions in parametric space inside which the characteristic function has the same number of zeros. Okay, so from this fact, we may formulate our problem as a constraint satisfaction problem. So the problem of finding stability crossing set can be formulated as constraint satisfaction problem because we are looking for theta and omega for which characteristic function equals 0. So omega is in R plus except a finite number of singularities, and theta varies in its parametric space. So the set of all feasible parameters, as you know, can be formulated this way. And this set S is a set, is a set inversion problem. So we have to deal here with the set inversion problem, and that's what we did using interval arithmetics. So finding stability crossing set is formulated this way. So we are having some omega and some parameters here that will generate, an f characteristic function, and we are looking for which values of f, for which values of omega and sigma we may, the characteristic function equals 0. So when you compute the image, the mapping of omega and theta using f, then for this particular problem, you have only two cases. Either 0 is a part of this box, or it's not a part of this box. So if 0 is not part of this box, then all omega and theta that were computed here are rejected. Otherwise, if 0 is a part of this box, then omega and theta are bisected and tested again until a precision is reached. Before reaching this kind of formulation, we have also tried to find the whole stability or the whole instability region by changing a little bit the formulation of the problem. So instead of having an A which is fixed to 0 or to some sigma for a given sigma, we've tried also to vary A in those sets in order to check for stability and instability. But it turned out in this latter case that this problem is an ill-posed problem because the algorithmic complexity is even worse than the brute force, because we have to test each individual parameter, to decide whether it's stable or unstable. However, the problem as it is formulated in the left-hand side is a well-posed problem, but only an outer enclosure of the stability crossing set can be obtained, because as you may see here in the second point, when you evaluate the mapping of omega and theta with f, it can never be a subset of 0. It's just the inverse that's true. Anyway, the problem is formulated using this as a constraint satisfaction problem. And I've provided here some introduction to interval arithmetic. So an interval is defined with the lower and upper set. So you may define some operations on intervals. This is interval width, interval vector constituted of multiple intervals. So basic operations, additions, subtraction, multiplication of intervals, and even division of intervals are already defined. However, those operations are not closed in the space of intervals. So when you evaluate a mapping of a given interval or a given box, then it's not always a box. So you have to provide an inclusion function, which usually introduces some pessimism. In red, you have minimal inclusion functions. Okay. So the CSP that we have proposed can be solved either using contractors. So here you have an example of contractors. So in case x1, x2, x3 are in these intervals, so applying a forward contractor means that you compute x3 with respect to x2 and x1. Yeah, so intersecting x3, you end up with smaller intervals. Anyway, all these things are already known to the community, I guess. There's another problem that may happen and for which we require bisection. So if the solution set is disjoint as it's shown here, then you have to bisect and carry on, solve the problem. So that's why there is an algorithm, the Sivia algorithm that we have used here, which was introduced by Luc Jolin and Eric Walter, 1993. So we have used exactly this algorithm. However, by computing only the outer enclosure, because it's not possible in our problem to compute the inner enclosure. Okay. So I may show you some results regarding the three problems that we have formulated before. So here is the distributed parameter system. So I've plotted the stability crossing sets for both cases, semi-infinite and finite aluminum rod. So we are getting those stability crossing sets. And then once you have this limitation, you may just compute a root at a given value, let's say when k equals 0 and tau equals 0. So you may conclude that this system is stable. And then straightforward conclusion, the system is stable for all values that are in this region with this limit here for the semi-infinite rod and with the blue limit for the finite rod. Yeah, if you remember, for this distributed parameter system, we have computed the root locus and we end up with the conclusion that the system becomes unstable in the particular case when tau equals 0, when it becomes unstable for k equals 56,000. So this result may be seen here also. So when tau equals 0 for 56,000, so it's exactly this point, the system becomes unstable. So this was the only analytical solution that we had. But using our method, we have just computed all the solutions for any combination of k and tau. Here are the poles crossing. So again, in red, and these red squares correspond to plus or minus something like 0.05, which is exactly the frequency that's here, plus or minus 0.05. Okay, so yeah, our algorithms converge after some 40,000 or 73,000 calls, depending on semi-infinite or finite rods, in about in less than half an hour. Okay, for time delay system, we obtained just the same thing. So first of all, we started for distributed delay system. Remember, characteristic function is this one. So we end up with this red plot. So outside this red plot, we have 0 unstable poles. However, we must be very careful when we have 0 unstable poles, especially for some other irrational systems. It doesn't mean that the system is stable. So what our algorithm does is just it guarantees that it has zero unstable poles, which means it doesn't have, it is not exponentially unstable. And then if you remember, we studied also, if we, instead of looking for the poles which are to the left and to the right of the imaginary axis, if you look to another axis, so we have chosen another vertical axis, which is minus 0.02, and we have plotted the stability crossing set with respect to this new vertical axis, and we obtain this blue plot. I didn't plot down just for, because we only need, in fact, this limitation. And what we may say here that we guarantee stability, exponential stability of order minus 0.02 outside this blue curve. Yeah, so everything converged in about 72,000 calls of the CV algorithm. We did the same thing for the retarded type time delay system. So again, we plotted stability crossing sets. And we did also the same thing for fractional domain system, for fractional order systems. And we guarantee here, for instance, stability of all fractional systems that have commensurate or even incommensurate orders that are here in this region. And outside this region, we guarantee that there are at least, there are exactly two exponentially unstable poles. So we did it for two kinds of initializations. Here is second initialization, which is very similar. I mean, the first one was just limited in here, and the second one goes to 14 and 620. So here are the number of unstable, exponentially unstable poles in each region. If you remember the root locus, when alpha 1 equals 1, we concluded on instability for alpha 2 equals 2.8. So if you take the vertical axis, alpha 1 equals 1, the first instability appears right at 2.8. The second one appears around 7. So here it is 6.7. So it was a way for us also to conclude on the exactness of our results. So I'm about to finish. Here are the conclusions. So a universal framework has been proposed for studying exponential stability for linear irrational systems. I mean, for many different kinds of irrational systems that fulfill the three hypotheses that I showed you. So to reach this result, first of all, we started by extending Dieudonné's theorem to non-compact sets. This is something that is necessary, especially for irrational transfer functions which have some branch points on the imaginary axis. And by extending this theorem, the only way for the number of roots of characteristic function to change is by crossing the imaginary axis. So then we have determined all these crossing sets for which values of parameters we obtain this crossing. So on this basis, a robust algorithm based on integral arithmetics has been proposed for determining those stability crossing sets. So as I told you in the beginning, these are quite new results that are not published yet, that have been submitted, but anyway, that are available on HAL, which is a kind of French archive. Danke.
Okay, merci beaucoup, Rachid, and thanks a lot for your very inspiring and very clear presentation. And I think now, yes, the first question already has been raised by Luc.
Yes, thank you for the talk. It's very interesting. You can hear me, yes?
Yes, yes.
Yes. Okay, so it's about the crossing set. So the crossing set is a subset of the set of all parameters, yes? Or
right.
It includes S also?
Right. It's a subset I mean, here the set of all parameters, let's say the searching set is from 0 to 15 for alpha 1, from 0 to 20 for alpha 2, and the stability crossing sets are inside those red curves.
Okay, and you said that it was not possible to have inner approximation for this set because this set has a given area. It's not of zero measure.
It has actually a zero measure because the width of the set is 0.
Ah, okay, that's what I don't understand. Because to me, it was the set of all parameters such that there exists S such that the characteristic function f of S and P equal to 0, something like this.
Right.
So my feeling, it was that since f is a complex function, to me, it could have some volume, this set, no?
F is a complex function, you are right. F is characteristic function. So if you map omega and the parameters with F, you are looking for the values of F that equal 0.
Okay, I understand. So it has a zero volume.
So
okay.
It has a zero volume. This is right.
Okay, I understand. That's all. That's all. Otherwise, all was clear. Thank you.
Thank you, Luc.
Thank you.
Okay, do we have any other questions? Maybe since Luc just asked this question, I would like to go back maybe to the slide 38. Yes, and I think, maybe Rachid, you can correct me, but I think one further advantage of your formulation also on the left-hand side is that you do not have any problems in such cases when the parameter dependency leads to a pole that is touching the imaginary axis, and a slight modification of this parameter then leads immediately to not cross the imaginary axis, just to go back into the stable domain again, because those are also points that you do not lose in such a way. And I think you would lose such kind of points. There are, yes, marginally stable points. Those are points that you would lose maybe when going to the right-hand side of the slide.
Yeah, but in this case, let's assume, yeah, in this case, if the point touches the imaginary axis, then it's included in the stability crossing set. Then you will plot a stability crossing set anyway, but you have to compute here at a given point what is the number of unstable zeros.
Yes, and then on both sides you have the 0.
Yeah, you may find on both sides 0. This is right.
Yeah. Yeah. And that's, I think, a really nice property here due to the fact of using the CVR algorithm, that those are points that you will never lose.
May I ask a question if Luc is there?
Yes, he has raised also his hand again.
Maybe he forgot to
okay, let's see.
Yes, so, yes, I am here, but I will have to remove the hand.
Okay.
I had a real issue for another example because I was obliged to choose some precision which is greater than this one for another example which is not presented here. So I've chosen precision divided here by 2 to the power 10 because just the curve was a little bit ugly, so I needed some more precision in here. And the point is that, okay, MATLAB did calculations in about half a day, and MATLAB was not able to plot it because I had many intervals to plot. So MATLAB was not able to plot it. So I was wondering whether you have any solution for this.
No. I think maybe it's not the best way to use boxes. I don't know. Using boxes here for the boundary you want to approximate is probably not the best. but I never meet this kind of problem. But indeed, it could be interesting to find the way to represent the subpathing enclosing this from this boundary.
Okay, without boxes.
I have no idea. I don't know. I don't know.
I was thinking maybe some of the routines that you are developing. So you're doing it with the Python. Maybe Python would be able to plot it. I mean, actually, I'm just using MATLAB and MATLAB.
It's possible. We use usually. Yes, usually we use vibes to draw a lot of boxes, but I think anyway you will be limited one day by the number of boxes. Sorry.
Okay, thank you.
Okay, do we have any other questions? Okay, I have a second question. And you mentioned at the very beginning also those irrational transfer functions. And yes, the type of transfer functions that you had shown, those are directly, for example, those that you would obtain, for example, when using Warburg elements for modeling battery systems. And do you have investigated, let's say, more or less some kind of a dual task? Because at the moment you're investigating the stability of a given characteristic function. If you have, for example, some real-life application, let's say a battery, you know that your system doesn't have any unstable poles. Did you use this to parameterize maybe or to identify parameters of such irrational system models that have guaranteed stability properties?
Yeah, but this is, I mean, disconnected from the actual work. So this is an identification problem where you might set some constraints on the identified variables.
Yes, at the moment you have those constraints on, let's say you are alpha 1 and alpha 2, for example.
Yeah.
And when you're identifying additionally some parameters in the system, for example, just look at your characteristic function there on the top left. For example, when you want to identify this parameter +1 or +2 in the expression. At the same time, then just performing a CVR type routine would immediately lead to an explosion of complexity there, because you have to bisect on the one hand, yes, those orders, the alpha 1 and alpha 2, and on the other hand, also parameters to identify. Do you have any idea how to combine this?
From identification perspective, including stability from identification perspective. We have Andreas to think about it. I don't have any ready solution. What we did is some frequency domain identification, because it's a little bit easier when replacing S by J omega and doing some frequency domain stuff. This is something that was done, but with no explicit constraints regarding stability. But why not? This seems to be an interesting problem.
I think at the end it must be something that maybe adds in this kind of constraint satisfaction problem some further constraints in some kind of contractor technique, that you're cutting off the domains that are not reasonable, and yes, that you rapidly you start to contract the domain in such a way that you're only searching and bisecting in domains that really make sense.
Yeah, sure. And assume that the measurements are with intervals. So this might be done. Yeah, also, so you combine stability and also other constraints that the model must intersect at least all the measurements. This is really interesting. Yeah, that might be done.
Okay, Luc.
Yes. I have another question. I see that your boundary in red is quite thick. Did you use a centered form for your to contract or to test your boxes?
Yeah, actually, I've tried, particularly for this example, I've tried using the forward-backward constructor. I've tried calling forward-backward constructor at each step of the CV algorithm. And it turned out that, yeah, it converged in less iterations, in less calls of CVA. But if you compare the time of convergence, then, yeah, we're requiring more time to converge. So, yeah.
But
this one, I've used contractors in this one in particular, but since it required more time to converge, I just left aside the contractors and I only used the CVA in here.
Okay, but to me, if you use a centered form, probably you will be much more accurate with much less red boxes.
By central form, you mean representing a complex variable with disks, right?
You need to use a derivative. So I don't know if it's quite easy here because you have to compute the Jacobian of your function f, but normally your boundary should be thin, not thick like this.
Okay.
Maybe if I think it's quite easy to test it.
Do you have any reference on this centered form?
The centered form, maybe I could try to do it if you send me. But the centered form, yes, it is in the book of Moore. Okay. The centered form is minimal if your box is small, which is the case here for the red boxes.
No,
it will be really there is no more pessimism.
Okay, yeah. I'm really interested in this.
It's very easy to use, very easy to implement. The centered form.
Do you want to test it on this, or?
I could test it if you have. So I need the expression of your function f, the exact, and after I have to compute the derivative. I think I could test it. Yes, it would be quite easy. I could test your example. You just have to be sure that I have the good equation. Yes, I can test it quite easily.
Do you need derivatives with respect to alpha?
Yes.
Okay. So
the Jacobian with respect to
alpha 1, alpha 2, to both parameters here.
Yes, something like that.
Yes. Okay, so I may send you this, and I will compute the derivatives so that you have everything.
Yes, I could. The function U inverse. Yes, I need the function U inverse.
Okay.
Okay. Good.
Do we have any other questions? Okay, this doesn't seem to be the case, but I think we already had lots of discussions and also some ideas, for example, the centered form discussion, or also the identification discussion, which stimulates hopefully a few aspects for further work. And from that point of view, many thanks again, Rachid, for your very interesting talk. And I was really glad that you gave the talk today. And yes, the only thing that is now remaining is to wish everyone a remaining nice Friday afternoon. Have a nice evening, weekend, and see each other again soon in Friday in 2 weeks when we will continue our seminar.
Thank you.